So in this video, I'd like to continue the previous topic. I showed you some standard derivatives, and I told you that we were going to cover rules of differentiation. And the goal is that at some point, after a couple of the next videos, we will be able to calculate derivatives of some crazy functions, even like this one here at the top of the screen. Because I already showed you 5 standard derivatives, but we haven't done too many rules yet. We know how to differentiate x to the power of n, we don't know how to differentiate e to the power of x, but we don't know how we can differentiate composite functions. We don't know how to differentiate functions which are built out of these individual functions here. But it is safe to say that we did cover one of the rules. We can call the fact that if we differentiate a constant that is independent of the argument with respect to which we're differentiating, d dx here, then we always get 0. Because a constant does not change with the argument, the rate of change is 0, the gradient is 0, it's a straight horizontal line, the value of the derivative is 0. The second rule I want to look at today is what happens when I differentiate a sum of two functions. So I'll have two functions of x, f of x and g of x. I'm going to add them together and I want to differentiate the sum, so the result. So this is going to be some other function, let's call it h. And the function h is the sum of functions f and g. What is going to be its gradient compared to the individual gradients of these two functions? So now pause for a second and try to think about what the result might look like, and maybe even try to justify it, maybe visually. We'll do it in a second together. Okay, so I have 3 graphs here. I just drew some straight lines, some functions on a graphical calculator. This one is, I believe, a straight line y equals 1¼ x. And this one is y equals 3/4 x. And this one? Well, I added these two functions together. So basically, I added these two algebraic expressions together. 1¼ x plus 3/4 x equals 2x. Yeah, this is nothing crazy here, right? We know that if I add 1.25 and 0.75, I get 2. But think of these as functions again, and think of their gradients. 1.25 was the gradient of the brown function, 0.75 was the gradient of the purple function, and 2 is the gradient of the sum of these two functions. Where did this number come from? Well, 2 is just 125 plus 0.75. So if I call this function f of x, its gradient, its derivative, so f prime of x, to remember different notation, is going to be 1.25. That's the value of the gradient. If this is g of x, then the gradient of g of x is 0.75. And how did I get this function, this blue line? Well, we said that this blue line was the sum of the functions f of x and g of x, and let's call it h of x for now. What is the gradient of h of x? Well, it's the number 2, which was the sum of this and this, which was the sum of f prime of x, the gradient of f, and the gradient of g. And this trivial rule of addition applies basically to any function, doesn't have to be straight line. If I have some 2 smooth functions with gradients like these, and say for this x, this function has a gradient of a half, and this function has a gradient of 2, then if we were to sum these two functions up, the gradient for this x would be 2.5. So what is the conclusion here? Because it's pretty simple. The realization that we've just come to is that the derivative of the sum of two functions is equivalent to the sum of the derivatives of these two functions individually. In other words, gradients add. So some things that are quite obvious but actually very useful that follow from here. Let's think about what happens when I add a couple of functions that are the same. Let's take x squared and add it 3 times. X squared plus x squared plus x squared. Now let's try to differentiate it. So let's ask what the gradient is of a function, which looks like this. And we know that it's going to be the gradient of x squared plus the gradient of x squared plus the gradient of x squared, 3 times the same thing. What is the gradient of x squared? We already know that the derivative of x squared is 2x. We even derived it from first principles. So let's use it now. So as I already mentioned, I'm getting 3 times the derivative of x squared individually. And obviously I could have written this in a different way and it would be the same thing if I just said that I was differentiating 3x squared. Yeah, these two things are obviously equal and I would need to get the same result, 6x. But now let's look at this form. Where did this 3 come from? Well, this 3 came from the fact that I was differentiating a sum of 3 functions, x squared. And this thing here was just the derivative of one of them, of x squared. In other words, if I use even more colors now, it should be pretty clear that if I differentiate a function that is multiplied by a constant, I can say that I'm getting the constant times, so in this case 3 times the derivative of this function individually. And some people say that we can basically take the constant out to the front and then we would be writing it like this instead. And if it was obvious to you, that's fine. And let's just appreciate that all this was the result of this simple statement here. And now we're ready for our first example. So I've copied and pasted the things that we've learned so far in this video series, and now we'll be ready to calculate the derivative of a polynomial. We could even use the one from the big example here. So it was x squared minus 3x plus 1. And we would like to differentiate it. Okay, we already know that the gradients add. So we know that if I differentiate a sum of functions, this function consists of 3 terms. I can basically differentiate each of the terms individually and add the gradients up. Okay, so the sum of the derivatives of these 3 terms individually. So I already know that the derivative of x squared was 2x. We can either remember this from first principles or we're using this rule here, this standard derivative. The 2 goes to the front and the exponent goes down by 1. So instead of being x squared, it is now x to the power of 1. So you have 2 times x to the power of 1, which is just 2x. What's happening here? Look, I explicitly said that I'm adding another derivative, and the derivative that I'm adding is the derivative of negative 3x. Again, let's say that the function here is x to the power of 1, and this is just a constant that is standing in front of it. So I can keep the constant as it was, negative 3, and then just differentiate this function. And this function is just x to the power of 1, so if I bring the 1 to the front and decrease it by 1, I am getting 1x to the power of 0, which is just 1. So I'm multiplying by 1. But hopefully you would have already realized that this is basically just a function of a straight line. This is just a straight line with a gradient of negative 3. So we didn't really need to do all that, but I just wanted to show you how those rules would basically still apply, even if the exponent was just a 1. And how about the derivative of number 1? Number 1 is just a constant, so we know that the derivative of a constant is always going to be just 0. The value of number 1 does not change as we change x. It's independent of x, so it's just 0. So what do we get in the end? In the end, we just get 2x minus 3. And the final example, we're differentiating something like this. This function looks a little bit different than just a simple polynomial, but we'll be using the same exact rules that we have just used in the previous one. So let's do it a bit more quickly now. I need to find the derivative of this thing, and this thing separately. What is the derivative of 7x to the power of 5? The 7 is just a constant, so I'm just going to leave it at the front. And now what's the derivative of x to the power of 5? Well, it's going to be 5 times, the power goes to the front, 5 times x to the power of 1 less than 5, so x to the power of 4. Yeah, the exponent goes down by 1. And then, what is this? This is some square root. What is the square root? I don't have square roots here. How am I going to deal with this? All we need to do is realize that a square root can also be written as a power, x to some power. To be more exact, to be more precise, this thing is negative 3 times x to the power of a half. So this is pretty similar to this case. Let me differentiate it. This is a constant that multiplies my function, so it stays at the front, negative 3. And now what's the derivative of x to the power of a half? It's going to be half, exponent goes to the front, half times x to the power, which is 1 less than a half, so a half minus 1, this is going to be negative a half. And last part, what is this? We need to treat it the same way we treated square root of x. 2 over x to the power of 5, we can write it as 2 times x to the power of negative 5, and we've solved our problem. So here the 2 stays in the front when we're differentiating, and then minus 5 goes to the front. I need to multiply, so I'm just going to put it in brackets, and I have x to the power of the exponent 1 less than 5, so be careful, x to the power of negative 6. Yeah, I'm subtracting 1 from negative 5 and I get negative 6. So this is the result. Obviously I can simplify it a bit. And if you want, I can even write it like this. But we have just differentiated this function here. Congratulations.